In this video, I'll talk about transformer turns ratio. Some people in industry will refer to it as TTR test. This is an important test, because the way transformers work is, induction, electromagnetics basically, and you have turns on the high side, turns on the low side, and that's how you kind of transfer from one voltage to another. If the number of turns are not correct, then you're going to affect the voltage, the ratio. So this test, TTR or transformer turns ratio, checks for open circuited turns, checks for shorted turns, checks for inadvertent added or missing turns, because sometimes mistakes happen, one turn, two, or basically could mistakenly be added, due to whatever, reason. But this test will check for that, at least hopefully. So things that can affect the test. So test voltage, So while a winding may be rated 138 kV, for instance, TTR test will be applied at very low voltage, because you can't apply 138, it's not realistic. So, but how high can you, because since it's a low voltage that you apply during this test, but how low can you go before you jeopardize the accuracy of the measurements and make sure that what you're measuring is correct. So I'll talk about that. Applying voltage to high versus low side, so test voltage. That's can affect the test, the turns ratio, and I'm talking about the TTR, transformer turns ratio. So applying voltage, because you have high side and you have low side. Well, should I apply to the high side or the low side? So that can make a difference. Applying single phase versus three phase. If you have a three-phase transformer, should you do single phase or do three phase? Single phase means you measure one phase at a time. Error of test will be reduced if higher voltage is applied. So this kind of goes back to here. So obviously the higher the voltage you apply, the better the accuracy of the results. Error of test will be reduced if you apply from low voltage versus high voltage. Because if you apply to the low voltage, then on the high voltage side, you're going to have a higher voltage. So, but the problem, and I'll talk about that in a second. So low voltage is typically closer to the core in core form, because if you take like a cross-section area, so if this is the core limb, for instance, and wound around this limb, and I'm not showing top yoke, I'm not showing bottom yoke, I'm not showing the other two limbs, so I'm just showing one. You're going to have, if you kind of like look at it from a cross section, you're going to have low voltage winding. Then you're going to have some gap between them for insulation purposes. Then you're going to have the high voltage. So because low voltage is next to the core in core form, better flux distribution, and you have better flux distribution and mutual flux. The mutual flux that links the two windings is better. So that's why applying the voltage to the low voltage is better. But there is a safety concern with that. So test is applied from high voltage for safety purposes. Because when you apply a voltage to, I guess I'm going to talk about here. So let's assume you have a 138 kV grounded Y to 30.8 grounded Y kV transformer. If test is applied at 13.8 kV side, in other words, you have a grounded Y. So this is rated 138 kV. So you would have H1, H2, H3, and this one HO. Then the same thing with the low voltage, so you have X1, X2, X3, XO. So if test is applied to this side here, so this is the HV side, this is the low voltage side, say 200, let's say 200 volt AC. So you have to apply AC voltage. Then 138 side would see, because you know the ratio, you know, if you take 138, in this case we don't have to worry about converting to line to neutral because both are grounded, are Y, and so the two voltages are line to line, so it doesn't matter in this case. So if you take 138 divided by 13.8, that's a ratio of 2, sorry, a ratio of 10. In other words, 138 kV divided by 13.8 kV cancel out. In reality, you know, you should divide it by square root of 3. It's always better to do it in per phase, you know. But in this, like I was saying, in this case, both are Y, both are line to line, so it doesn't matter. so the ratio is 10. So I'm applying 200 volt. That means the high voltage will see 2000 volt AC. Well, 200. Sorry, 2000 or 2 kV, that's high enough to cause all kind of issues, you know, so that's dangerous to the equipment and also to the personnel applying this or doing this test, or, you know. So that's why, while you get better results if you apply the test to the low voltage, but for safety reasons, you know, it's typically applied to the high voltage, because even if the voltage is very low on the low side, 200 volt, but on the high side we'll see 2 kV or 2000 volts. So it can be dangerous, you know. So excitation current will be measured, you know, because you're applying AC, so the core will be excited, so you will have excitation current, so you can measure that, and it will be in milliamps because you are applying very low voltage. So by IEEE C5712.90, you know, 2 voltmeters. So there are different ways you can measure the turns ratio. So one way, so 2 voltmeters, you know, because you have high voltage, low voltage. So you want to measure high voltage and you want to measure low voltage at the same time. So one measures high voltage and the other measures the low voltage. The second set for readings shall be taken with instruments interchanged, and average of the two readings is taken to compensate for instrument errors. You know, so in other words, you swap the whatever you're using to, you know, the voltmeters, and, you know, then you repeat the measurements. So you can, that way you can, when you average the two, that way, because you have a voltmeter on the high side, a voltmeter on the low side, but if you swap them and you take another set of measurements, then you take the average, at least you can remove instrument error, you know, any error introduced by the instruments, measuring instruments. Should get similar readings with the two sets. Obviously you want to have similar readings, you know. At least 4 tests with voltages in 10% steps. The average result is considered the true value. Because since you're not applying close to rated voltage, you know, you're going to have some errors, you know. But by doing these steps, at least, you know, you kind of get true value, close to true values, you know. The value should check within 1%. In other words, these values here, if not, other voltmeters should be used. So the turns ratio, so by IEEE C5712.90 for the turns ratio tolerance, the turns ratio or ratio shall be within 0.5% of the nameplate voltages. Because if you have taps, you're going to measure the turns ratio at each tap. For transformers with LTC, low tap changer, and preventive auto transformers, or also known as PI, the ratio in the bridging positions, odd numbers basically, may exceed tolerance if a low voltage is applied. So that's something you want to keep in mind. So in other words, if you have the regulating winding for the tap changer, so you're going to have turns and so on and so forth. So you're going to have, if you have like 32 taps, 16 above and 16 below, with you know, and you have 10% above and 10% below voltage change. So if you do with the PA, actually you just need 8 taps basically. So 8 of these guys. So this is a regulating winding. So then you have the tap changer will have the selector. So these are the contacts connected to the taps. So when you are in a bridging position, in other words, you have 2 taps. So this is, in other words, this is 1 tap. This here is the second tap, or let's say tap 2, for instance. Sorry about that, tap 1. So when you bridge the 2 taps, so you have, these are turns, number of turns in between them. So you're going to have what they call the reactor, the PI basically. So this is the one section or half of the reactor, or also PI. And you have the other section. And you're going to have a vacuum bottle, you're going to have bypass switch. There are other things to the LTC that I'm not showing. But the PI is there because you are bridging the 2 taps. Now you're going to have circulating current because the 2 taps are different voltages. So when you have, so in this situation, basically tap 1, 3, 5, 7, 9, 11, 15, then, you know, in the raise, so this is either, so it's in the raise direction and also in the lower raise. In other words, when you tap up or you tap down. So these odd number taps, which are in the bridging, basically are bridging 2, because in the bridging 2 taps, in the even numbers, the two selectors will be on the same tap. In this case, the PI is not excited, so there is no, it's not an issue. So this is so when the PI or preventive auto transformer is excited, in other words, the tap changer selector switches, the 2 kind of selectors are on 2 adjacent taps, the PI will be in the circuit, and if you are applying a low voltage, you might exceed that 0.5% tolerance. So that's due to the excitation current possibly affecting the result. One way is to take the average of the adjacent non-bridging. Non-bridging means it's when the two selectors are on the same tap. So basically, it would be the even. So 2, 4. So you basically, if this is, actually, let me take that back. So let's see. But basically, in non-bridging, when the tap changer is not in the bridging position, you take the average of the 2 non-bridging that are kind of adjacent to that tap. Then you take the average of that, and it should be within tolerance. So for instance, for 15R, so that's an odd number. That means it's bridging where the LTC or low tap changer will bridge 2 taps, take the average of 14R and 16R. So because you're going to have 15R here, next to it you're going to have 14. Raise means, R means raise, like it's the tap changer is raising the voltage. 15, then you have 16R. So whatever you measure here, 15R, since it's a bridging position, it might exceed that 0.5%. So what you do, you measure the turns ratio at this position, you average them, and if it's within tolerance, you say that's fine. So measure ratio on all taps. So if you have low tap changer, you know, that's a lot. It's a lot of taps, but that's the only way you can guarantee that there is no issue with the tap changer, because sometimes you might only, per tap, you might only have 1 or 2 turns, for instance. A mistake might happen where if 1 turn is added, it's going to affect the results. So the only way you can check that is you perform the test on all taps. If you have a de-energized tap changer, you do the same thing. If you have a delta wire reconnectable, in other words, you have a switch where you can connect the windings as delta or as a Y, because the switch can do that. So measure in the delta, also measure in the Y. That way you're sure the ratios are correct. If you have a dual voltage, because you might have like a 2x1 or 3x1, for instance, you might have like, 12.47, for instance, kV, then you might want to connect. So if you divide that by 3 or by 2, let's see, so say like 4.16 kV. So this is, you have like in a distribution system, you have 12.47 kV, for instance, you have 4 kV, and you want to buy a spare transformer, and you want to maximize, instead of buying like 2 different spares, you say, well, what if I buy 1 spare transformer and I'm going to store it? Then that way, if I have a transformer that fails on the 12 kV side, I can use this spare. If I have a transformer that fails on the 4 kV side, then I can use this spare. Then you have a dual voltage switch, which you can basically, just by changing the position, it will configure the windings properly for you. So in that case, you want to measure, and in this case it matters a lot, because if you have an additional turn, when you change from 12 kV to 4 kV, it's gonna put some sections in parallel. What's gonna happen? You're gonna have circulating current and extra losses, basically core losses and other things. So it's important to measure the turns ratio in all winding configuration, basically. So typically a voltage in the range of 100 to 250 volt AC is applied to the high voltage side. So you can see if you have a very high voltage, 345 kV, for instance, line to line, it's going to have a lot of turns. So the accuracy basically will go down, if you apply like 50 volt or 40 volt, so as you increase that voltage, the accuracy goes up. And also, you don't want to go beyond that, because again, for safety purposes. And some equipment, they can actually, they might have like some control where, so as not to exceed that 250 volt AC, But again, it's for safety purposes. So here's just an example. So 138 kV, grounded Y, 13.8 kV, grounded Y. Number of primary turns is 1,000. Number of secondary turns is 100. One thing to mention, so TTR, or turns or transformer turns ratio, is really a voltage ratio, because if you remember if you go through the ampere turn and Faraday's law and everything, we say that primary voltage divided by secondary is equal to the number of turns in primary divided by number of turns in secondary. But when you are measuring the turns ratio in the field, for instance, you may not know the number of turns, So that's why you perform these tests. You're applying voltage, but it will still kind of tell you if the turns are within tolerance, So let's assume we have 2 taps at 2.5%, above and below on the 130 kV side. So what that means is, if nominal is 138 kV, and again, I'm showing line to line, you can do it on line to neutral. So then 1 tap above is 1 times 2.5% is 2.5%, it's a plus. So it's 1.025 times 138, it's 141.45 kV. if you have two taps, at 2 times 2.5 gives you 5%. So it's 1, because it's 1 plus 0.05 per unit, because it's 5%. Or if you want to think of it in terms of, you have the 100%, which is the nominal, then you're going to add to it 105% voltage. So, sorry, it should be just 5%. You're going to add 5%, so which is 105%. If you are thinking in terms of 5%, if you want per unit, you divide 105% by 100, which is 1.05 per unit. So that's what you see here. So if you go down, then you're going to subtract 2.5% or 0.025. So which is 0.975 times 138 kV, you get 134.55 kV. 2 taps, which is 2 times 2.5, you subtract 5% basically, so it's 138.1 kV. So nameplate TTR in this case, since in this example I gave turns, so it's 1,000 divided by 100, which is a ratio of 10. To step down from the high side to low side, or if it's step up, to step from low voltage to high voltage, you're going to multiply by 10. So nameplate voltage ratio, so I'm going to take the high voltage divided by root 3, so this is just square root 3, because again, it's always better to do it in per phase. That way you're not off by a factor of root 3. Then you do the same thing here, so it checks. So now let's assume, okay, so it's the same example. I just repeated these here. So now we calculated that. Now let's assume the measured TTR is 10.01, which is off by 0.01 from the nominal. So is that okay? So if you take the difference, which is the nominal, 100 times what you've measured minus the nominal divided by nominal or nameplate, you get 0.1%, which is still less than 0.5% tolerance, but you still need to verify, make sure it's okay. Now, again, this is just a hypothetical example. It's not an actual. It's just to give you an idea. So now, if I take that 0.1% times 1,000 turns on the primary, it gives me 1. That means in this scenario, probably, I'm just investigating basically. I'm just kind of showing like some investigation techniques here. So that tells me there is 1 extra turn on the high voltage side. Now I'm going to do the same thing to the low voltage. 0.1% times 100, because I have 100 turns on the low voltage. So it's 0.1 turn on low voltage. That 0.1 turn does not make sense. So probably there is some issue with the high voltage. There is an extra turn. And that's where you kind of do other things, like make sure, because just because it's within tolerance, you don't want to assume it's okay. You want to make sure, it makes sense, because just because the difference is small, it doesn't mean that it's not worth investigating. So remember, voltage ratio is the ratio of high voltage phase voltage. In other words, it's line to neutral. If you have a Y, and LV phase to neutral. Here's an example. If you have 34.5 delta and 13.2 grounded Y, nameplate TTR, because this is delta, we know in a delta the phase voltage is equal to line voltage, or line to line. So that's why you take 34.5 kV divided by, because the low voltage is a Y, then I have to divide by square root 3. So the ratio is 4.526. You do not want to take 34.5 divided by 13.2. This here would be incorrect, because you're going to be off by square root of 3. So always take the phase voltage. That's why If you get in the habit of using phase voltage, then you will never make this mistake. But if you use the line-to-line voltages, that will only be correct when you have when you have grounded Y on the high side, grounded Y on the low voltage, or you have delta on the high side, delta on the low voltage. But to be consistent and you don't have to worry about it, just use phase voltage, line to neutral if you have a Y. So in terms of a connection, so let's assume we have H2, H3, HO, X1, X2, X3, XO. So basically you would apply high voltage, AC, let's say 250 volt AC, but again, you don't want to apply 250 if the winding is rated for that too, because if it's a very small transformer, you want to be careful not to exceed the withstand of the winding. So always you want to be careful about that. So then what you do, you apply voltage here, so single phase for in this case. Then you have a voltmeter. So voltmeter, I'm going to call it VH. They're going to connect it. Then you're going to take the same phase. So I'm going to call that VX. Let's call it VX. Then you're going to connect it to X1, then to neutral. Then what the TTR equipment will do, basically the turns ratio in this case would be VH divided by VX. And the equipment is calibrated because it's going to ask you questions. What is your connection, delta Y or YY or whatever, and voltage, and it will do some checks like internally. And also some of these TTR equipment, they can actually even do a check for phase displacement. In other words, for instance, if you have a delta Y1, for instance, where the delta is the high side and the Y is the low side, and the high side leads, so the delta side leads the Y by 30 degrees. So some TTR equipment, they can actually check for that too. So, but in this video, I'm just talking about the transformer turns ratio. Thank you and have a great day.